Here we go with part 2 of our curve sketching. I recommend that you watch the part 1, which is lesson 5 for polynomial functions first. We're going to use the same algorithm here to do a rational function. All right, so this time we have this rational function to work with. And as we did before, we're going to consider looking at the function itself before we consider its derivatives. So what can we learn from the function? We can start with intercepts. So we can get an x-intercept. So where the numerator is 0. And we'll get x equals 4. And of course, we can find the y-intercept by evaluating at 0, which gives us -4 over -2, which is 2. So that's already given us a couple of points. I'm going to find a couple other things before I worry about coming up with a scale, because we also know that we can figure out the asymptotes from the function as well. So we know that vertical asymptotes come from the denominator because we cannot divide by 0. So we're going to consider asymptotes as well. I'm going to label this just to make it a little easier for everyone to follow the work. You should consider doing this too. And this denominator is nice and factorable. So we get asymptotes at x equals 2 and at x equals -1. And now we need to consider what kind of horizontal or oblique asymptote this is going to have. So we're going to consider the limit as x approaches infinity. What happens to the behavior of this function? And some of you may recall that because we can see the denominator is going to grow faster because it is a higher degree than the numerator, we can right away see that this limit is going to evaluate to be 0. But if you need some of that confirmation to double check, one of the tricks was to divide all terms by the highest power in the denominator. So we can consider this to be equivalent. Because now those pieces we actually can consider the limit. So the limit as x approaches infinity for the first term, well, it'll be 0 because it's going to approach 0. Minus, again, 0. It'll also approach 0. And then the numerator, x squared over x squared is 1. And then minus x over x squared, well, that'll approach 0. And the next one approaches 0 as well. So we get 0 over 1. In other words, the limit is 0. So just in case you needed some convincing there, our horizontal asymptote will be y equals 0. So now I can make a bit more of an educated guess in terms of what I want to have my scale be. I'm kind of going to guess that there's going to be some things possibly out on the wings that we need to have as some critical points. So let's just go with a 1-to-1 ratio for our scale. And now we can plot our intercepts. So we have a y-intercept of 2, we have an x-intercept of 4, and we have asymptotes. At x equals 2 and x equals negative, whoops, -1. And then, of course, we know that the axis is going to be our horizontal asymptote. So now we can go forward and consider our first derivative. Although we can consider a little bit the behavior, right? We can look at our behavior approaching those asymptotes. So we actually could see that if you considered the limits approaching these vertical asymptotes, so if we approach 2 from the left, for instance, we should be able to see that this is going to approach positive infinity. You can pick a number like 1.99 and substitute it in there, and it's going to be positive. And the same thing approaching -1 from the right side. So we could pick like -0.99, and that too will be positive. So we can start to make some conclusions about what the behaviors are going to look like approaching those asymptotes. So now let's look like at the outside of those. If we approach 2 from the right, so we can test with a value like 2.01, we're going to get a negative infinity for this one. So this is going to have behavior that approaches like that. And same thing from the left side of -1. Pick, say, -1.01. And that one is going to be negative infinity as well. So the behavior will look like that on that side. And of course, we can write those out just so when we come back, we remember at the limit x approaches -1 from the right. We deemed was positive infinity. And -1 from the left is negative. Two from the left is positive. 2 from the right is negative. And recording this allows us to show our thinking, right? We can see, if someone else was to read this, they could see why we concluded that those pieces would be there. Okay, so let's consider our first derivative here. Using the quotient law. And we're going to want to expand and simplify our numerator because we care about our critical points here, which, as you know, are points that are undefined as derivatives or 0. So for the zeros, we want this to be nice and simple. You can see that I'm kind of skipping some steps. I'm doing some of it in my head. If you need to show more steps, you can. Just remember now that we're also looking at trying to be a bit more efficient. You can see some of these solutions start to get a little long. So the fewer steps that you need to show, the better off, just because it makes your work a little bit neater. And now we can consider undefined points. We don't really need to think too much about in terms of critical points because we know that those things are what formed our vertical asymptotes. So we're not going to get extremas or anything like that out of them. So we just really need to consider where the derivative is 0 here. And you'll find that this numerator is not factorable. So we're going to resort to using the quadratic formula. Which does simplify a little bit. Here we'll get 4 plus or minus root 10. Now, of course, when we go to actually sketch these, we are going to just use their approximate values because there's no way we can sketch something this precise. And you will find that they are approximately 0.8 and 7.2. And then we want to know what those points are actually going to be on our sketches. So we need f at 0.8, which will be approximately 1.5. And the function at 7.2 is approximately 0.1. So those are points that we suspect are going to be extremas. And because this is not a polynomial, and so it's a little less predictable, we can now test these using our increasing and decreasing intervals. So we're going to set up our interval chart here. And we, of course, have to care about the asymptotes as well. And since the numerator is not factorable, I'll just use that as a whole factor, and then the denominator, which of course, because it's squared, will always be positive no matter what value you're testing. And then we consider what that tells us about the derivative in total and what it tells us about the function. So let's test with, say, -2. And that one will be negative, which means overall the derivative is negative. And so the function is decreasing in that interval, which we can kind of see confirms what we already thought we knew about the left side of that asymptote. And here we can test with 0. This one will also be negative. So this portion is also decreasing. Also kind of confirms what we already thought we knew for that part. We just didn't know the 0.8 value before this. And now we can choose 1. That one will be positive. So that portion is increasing. Again, kind of confirms what we already thought we knew. And maybe we pick 5 here. Will also be positive. So overall, this is positive. Tells us again that it's increasing, which again confirms what we already knew. Essentially, what we weren't totally sure of is what's going to happen next. So maybe we pick 8 or 10 and test that value. It'll turn out to be negative. So that means it's actually decreasing on that part. So it will turn out that likely we have a local min at 0.8 and 1.5. Will be a local min. And likely we have a local max at 7.2, 0.1. And we could, of course, continue on and look at the second derivative to consider concavity test, using that second derivative test to feel more confident that these are extremas and look to see if there's a point of inflection. But you can see that we're dealing with some numbers that are getting pretty small here. And the most likely place to have a point of inflection is can be probably somewhere further out than the 7.2. And because our value is only 0.1, there's really little value that the second derivative test adds to this, and also involves a lot more complex algebra. We're already at a quadratic over a quartic to deal with. So you could do that and it would turn out that there's a point of inflection at approximately 10.4. But all we're really going to do now is test to see what the behavior is like as x approaches positive and negative infinity, so that we can be confident about what it is going to do there. So let's consider approaching positive infinity for f at x. We already know that that's going to be 0. The question is it going to approach from above 0 or below? So you can pick any kind of large value there to test in x, and it will turn out that large values of x make the function f positive. So this tells us that it's going to approach from above. And then do the same thing on the negative side. Pick a large negative value, and of course we already know the limit's going to be 0. The question is it above 0 or below? So you're testing it and you're going to find out that it will stay below the axis on that side. So now I have the information I need to finish my sketch. So that'll approach the asymptote from below. This middle branch here goes through the intercept and the minimum point with our behavior, and on the right has to go through the x-intercept to this local max and has asymptotic behavior from above. So you can really see that finding an inflection point over there is not going to be all that useful. We can tell that it's going to have to change its concave down over here. Right, this part here you can see is really concave down. So it's going to have have that asymptotic behavior switch over concavities at some point. But these numbers are so small, it's really going to add nothing to our drawing.